Hello mga ka-tribes! Welcome to Daddy Brew TV. This is your host, the adventurous math teacher. So for today's lesson, let's discuss part 1 of lesson 2, quarter 4, the central limit theorem with replacement. Now, what is a central limit theorem? Let's define. If samples of size n, where n is sufficiently large, are drawn from any population with a mean and a standard deviation, then the sampling distribution of sample means approximates a normal distribution. Okay, let's have example. Consider a population consisting of the values 1, 2, 3, and 4. Question 1. Compute the following. A. Population mean. B. Population variance. And C. Population standard deviation. Question number 2. Draw the probability histogram of the population. To compute for the population mean, first, let's make a table for the population values. Observe that there are 4 observations consisting of the values 1, 2, 3, and 4. Okay, so let's get the summation of the population values. That is 1 plus 2 plus 3 plus 4 equal to 10. Okay, so we are now ready to define the population mean. So the formula is mu is equal to the summation of x over capital N. So let's replace the summation of x, which is 10, over the observation 4. That is now equal to 2.5. Now, to get the population variance, let's continue on our table. Just simply subtract the population value 1 to our mean 2.5. That is 1 minus 2.5 is equal to negative 1.5. Subtract 2 to 2.5, that is negative 0.5. Subtract 3 to 2.5, that is positive 0.5. And subtract 4 to 2.5, that is 1.5. Now, let's square the difference. The square of negative 1.5 is positive 2.25. Square of negative 0.5 is positive 0.25. Square of positive 0.5 is also positive 0.25. And the square of 1.5 is positive 2.25. Again, take note, once you square the difference, the result is always positive. Now, let's get the summation of x minus mu quantity squared, or the square of the deviation. That is 2.25 plus 0.25 plus 0.25 plus 2.25 is equal now to 5.00, or positive 5. Okay? Now, let's define now our population variance. Compute for letter B. So for our population variance, we will use the formula sigma squared is equal to the summation of the quantity x minus mu squared over capital N. So what is again the summation of our x minus mu squared? 5. So we will replace it by 5 divided by 4 observations. And that is now equal to 1.25. That is the population variance. Now, of course, to get the standard deviation, just simply extract the square root of the population variance, denoted by letter C. Sigma is equal to the square root of the summation of the quantity x minus mu squared divided by capital N. And that is square root of 5 over 4, or square root of 1.25, which is equal now to 1.12. And that is the standard deviation of the population. Now, the other way to find the population mean is by using this formula. Mu is equal to the summation of x times probability of x. Take note that the summation of x is equal to 10, and the probability of each population value is 1/4. And 10 times 1/4 is equal to 2.5. To draw the probability histogram, we need to define the probability of the population values. Okay, if the population value is 1, the probability is 1/4. The population value 2, the probability also is 1/4. The population value 3, the probability is also 1/4. And the population 4, the probability is also 1/4. Okay, so we need these two to construct our probability histogram. So our probability histogram looks like this. On the horizontal part, we have the population values 1, 2, 3, 4. On the vertical part, we have the probability of x. So as you can see, the histogram has a uniform distribution and does not approximate a normal curve. Why? Because the sample size n is equal to 1. Now, what if the sample size n is equal to 2? That will be our next example. Consider all possible sample size of 2 that can be drawn with replacement from the population 1, 2, 3, 4. Okay, question number 1, compute the following. A. Mean of the sampling distribution of means. B. Variance of the sampling distribution of the means. C. Standard deviation of the sampling distribution of the means. And question number 2, draw the probability histogram of the sampling distribution of the means. Okay, so to compute for the mean of the sampling distribution of the means, again, let's construct the table of the population value. To compute for the mean of the sampling distribution of means, again, let us construct the table for the population values with a sample size of 2 and with replacement. Okay, so there are 16 observations because 4 times 4 is equal to 16. Okay, so what are now our samples? Our samples are 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 1, 2, 3, 2, 4, 3, 3, 3, 1, 3, 2, 3, 4, 4, 4, 4, 1, 4, 2, and 4, 3. So let's get the sample mean of the samples. That is 1 plus 1 divided by 2 is equal to 1. 1 plus 2 divided by 2 equal to 1.5. 1 plus 3 divided by 2 is equal to 2. 1 plus 4 divided by 2 is 2.5. 2 plus 2 divided by 2 is 2. 2 plus 1 divided by 2 is 1.5. 2 plus 3 divided by 2 is 2.5. 2 plus 4 divided by 2 is 3. 3 plus 3 divided by 2 is 3. 3 plus 1 divided by 2 is 2. 3 plus 2 divided by 2 is 2.5. 3 plus 4 divided by 2 is 3.5. 4 plus 4 divided by 2 is 4. 4 plus 1 divided by 2 is 2.5. 4 plus 2 divided by 2 is 3. And 4 plus 3 divided by 2 is 3.5. Getting the summation of our sample mean, that is now equal to 40. Okay, so we are now ready to compute for the mean of the sampling distribution of mean using the formula mu sub x bar is equal now to the summation of the sample mean over small n. So replacing the summation of the sample mean, which is equal to 40 divided by the observation 16, the quotient is equal to 2.5. And 2.5 is the mean of the sampling distribution of means. Now, let's compute letter B, the variance of the sampling distribution of mean. So to determine the variance of the sampling distribution of mean, let's continue working on our table. Okay, so we will subtract our sample mean to the mean of the sampling distribution of mean, which is 2.5. So 1 minus 2.5, negative 1.5. 1.5 minus 2.5, negative 1. 2 minus 2.5, negative 0.5. 2.5 minus 2.5 is 0. 2 minus 2.5 is negative 0.5. 1.5 divided by 2.5 or minus 2.5 is equal to negative 1. 2.5 minus 2.5 is 0. 3 minus 2.5 is 0.5. 3 minus 2.5 is also 0.5. 2 minus 2.5 is negative 0.5. And 2.5 minus 2.5 is 0. 3.5 minus 2.5 is 1. 4 minus 2.5 is 1.5. 2.5 minus 2.5 is 0. 3 minus 2.5 is 0.5, and 3.5 minus 2.5 is 1. Let's square the difference of the deviation. That is now 2.25. The square of negative 1 is 1. The square of negative 0.5 is 0.25. The square of 0 is also 0. The square of negative 0.5 is positive 0.25. The square of negative 1 is 1. The square of 0 is 0. The square of 0.5 is 0.25. The square of 0.5 is 0.25. The square of negative 0.5 is positive 2.25. The square of 0 is 0. The square of 1 is 1.00. The square of 1.5 is 2.25. The square of 0 is 0. The square of 0.5 is 0.25. The square of 1 is 1.00. Getting the summation of the mean minus the mean of the sampling distribution of mean squared is equal now to 10. Okay, let's use this data to define the variance of the sampling distribution of mean, denoted by the formula sigma squared over or sub x bar is equal now to the summation of the sample mean minus the mean of the sampling distribution of mean squared, divided by small n. Replacing it, we have now 10 over 16, which is equal to 0.625 or 625 thousandths. Now, to get the standard deviation of the sampling distribution of means, just simply extract the variance of the sampling distribution of mean. That is now square root of 10 over 16 is equal now to 0.79 or 79 hundredths. Okay, before we construct the probability histogram of the population values with a sample size of 2, let us determine first the probability. But before we determine the probability, let's define the frequency of each sample mean. Now, there is one sample mean. There are two 1.5 sample means. There are 3 sample mean of 2. There are 4 2.5 sample mean. There are 3 sample mean of 3. There are 2 sample mean of 3.5. And there is 1 sample mean of 4. So therefore, the probability of the sample mean 1 is 1 over 16. The probability of the sample mean 1.5 is 2 over 16. The probability of the sample mean 2 is 3 over 16. The probability of the sample mean 2.5 is 4 over 16. The probability of 3 is 3 over 16. The probability of the sample mean 3.5 is 2 over 16. And the probability of the sample mean 4 is 1 over 16. Therefore, the probability histogram of the sampling distribution of means when the sample size n is equal to 2 looks like this. It can be seen that the sampling distribution of the sample mean is approximately normally distributed. Now, consider all possible samples of size 3 that can be drawn with replacement from the population 1, 2, 3, and 4. Then compute the mean. Okay, so let's construct also the table of the population values when the sample size is 3. So if it is sample size of 3, there are how many observations? There are 4 times 4 times 4, which is equal now to 64 observations. So, the samples of the population values with a sample size of 3 with replacement are 111, 112, 113, 114, 121, 122, 123, 124, 131, 132, 133, 134, 141, 142, 143, 144, 211, 212, 213, 214, 221, 222, 223, 224, 231, 232, 233, and 234, 241, 242, 243, 244, 311, 312, 313, 314, 321, 322, 323, 324, 331, 332, 333, 334, 341, 342, 343, 344, 411, 412, 413, 414, 421, 422, 423, 424, 431, 432, 433, 434, 441, 442, 443, and 444. Next is to get the sample mean of the following samples. So we have 1 plus 1 plus 1 is divided by 3 equal to 1. 1 plus 1 plus 2 divided by 3 is equal to 1.33. 1 plus 1 plus 3 divided by 3 is 1.67. 1 plus 1 plus 4 divided by 3 is 2.00. 1 plus 2 plus 1 divided by 3 is 1.33. 1 plus 2 plus 2 divided by 3 is 1.67. 1 plus 2 plus 3 divided by 3 is 2.00. 1 plus 2 plus 4 is divided by 3 is 2.33. 1 plus 3 plus 1 divided by 3 is equal to 1.67. 1 plus 3 plus 2 divided by 3 is 2.00. 1 plus 3 plus 3 is divided by 3 is 2.33. 1 plus 3 plus 4 divided by 3 is 2.67. 1 plus 4 plus 1 divided by 3 is 2.00. 1 plus 4 plus 2 divided by 3 is 2.33. 1 plus 4 plus 3 divided by 3 is 2.67. 1 plus 4 plus 4 is equal to 3.00. 2 plus 1 plus 1 is equal to 1.33 if it is divided by 3. 2 plus 1 plus 2 divided by 3 is 1.67. 2 plus 1 plus 3 divided by 3 is 2.00. 2 plus 1 plus 4 divided by 3 is 2.33. 2 plus 2 plus 1 divided by 3 is 1.67. 2 plus 2 plus 2 divided by 3 is equal to 2. 2 plus 2 plus 3 divided by 3 is 2.33. 2 plus 2 plus 4 divided by 3 is 2.67. 2 plus 3 plus 1 divided by 3 is 2.0. 2 plus 3 plus 2 divided by 3 is 2.33. 2 plus 3 plus 3 divided by 3 is 2.67. 2 plus 3 plus 4 divided by 3 is 3.00. 2 plus 4 plus 1 divided by 3 is 2.33. And 2 plus 4 plus 2 divided by 3 is 2.67. 2 plus 4 plus 3 divided by 3 is 3.00. 2 plus 4 plus 4 divided by 3 is 3.33. Next, 3 plus 1 plus 1 is 1.67. 3 plus 1 plus 2 divided by 3 is 2.00. 3 plus 1 plus 3 divided by 3 is 2.33. 3 plus 1 plus 4 divided by 3 is 2.67. 3 plus 2 plus 1 divided by 3 is 2.0. 3 plus 2 plus 2 divided by 3 is 2.33. 3 plus 2 plus 3 divided by 3 is 2.67. 3 plus 2 plus 4 divided by 3 is 3.00. 3 plus 3 plus 1 divided by 3 is 2.33. 3 plus 3 plus 2 divided by 3, 2.67. 3 plus 3 plus 3 divided by 3 is 3.00. 3 plus 3 plus 4 divided by 3 is 3.33. 3 plus 4 plus 1 divided by 3 is 2.67. 3 plus 4 plus 2 divided by 3 is 3.00. 3 plus 4 plus 3 is 3.33. 3 plus 4 plus 4 divided by 3 is 3.67. And 4 plus 1 plus 1 divided by 3 is 2.00. 4 plus 1 plus 2 divided by 3 is 2.33. 4 plus 1 plus 3 divided by 3 is 2.67. 4 plus 1 plus 4 divided by 3 is 3.00. 4 plus 2 plus 1 divided by 3 is 2.33. 4 plus 2 plus 2 divided by 3 is 2.67. 4 plus 2 plus 3 divided by 3 is 3.00. 4 plus 2 plus 4 divided by 3 is 3.33. 4 plus 3 plus 1 divided by 3 is 2.67. 4 plus 3 plus 2 divided by 3 is 3.00. 4 plus 3 plus 3 divided by 3 is 3.33. 4 plus 3 plus 4 divided by 3 is 3.67. 4 plus 4 plus 1 divided by 3 is 3.00. 4 plus 4 plus 2 divided by 3 is 3.33. 4 plus 4 plus 3 divided by 3 is 3.67. And 4 plus 4 plus 4 divided by 3 is 4.00. Now, to find for the mean of the sampling distribution of means, let us add all the sample means in each corresponding columns. For this column, the summation is 32. For this next column, the summation is 37.33. For this column, the summation of the sample mean is 42.67, and for the last column, the summation is 48. So using the formula, mu sub x bar is equal now to the summation of all the sample size, which is 32 plus 37.33 plus 42.67 plus 48 is equal now to 160 divided by the observation 64, and the quotient is 2.5. And notice that the mean is still 2.5. That is the mean of the sampling distribution of mean, or denoted by mu sub x bar, is equal to the population mean, denoted by mu. Before we draw the probability histogram of sample size 3, let's construct the frequency table. Now, for a sample mean of 1, the frequency is 1. A sample mean of 1.33, there are 3. A sample mean of 1.67, there are 6. A sample mean of 2.00, there are 10. A sample mean of 2.33, there are 12. A sample mean of 2.67, there are 12 also. A sample mean of 3, there are 10. A sample mean of 3.33, there are 6. A sample mean of 3.67, there are 3. And a sample mean of 4, there is 1. Okay, when we add this, of course, the total is 64 observations. Now, let's get the probability. No? Okay, the probability is 1 over 64 for a frequency of 1. For a frequency of 3, that is 3 over 64. For a frequency of 6, that is 6 over 64. For a frequency of 10, that is 10 over 64. A frequency of 12 is 12 over 64. A frequency of 12 is 12 over 64 also. A frequency of 10 is 10 over 64. A frequency of 6 is 6 over 24. A frequency of 3 is 3 over 64. And a frequency of 1 is 1 over 64. And as you observe or see, the probability histogram looks like this. Meaning, the sampling distribution of mean when the sample size n is equal to 3 is almost normal than the sample n equal to 2. In general, as n increases, the sampling distribution of the mean is almost a perfect normal curve. Okay? And that is the main idea about a central limit theorem. Okay? So much for this. Thank you for watching. See you on my next video. Bye.